The next category we're going to look at is alkyl halides. An alkyl halide is a carbon that's attached to a halogen, which is fluorine, chlorine, bromine, iodine. And there's different classifications just like we had with alcohols. So if the CX is attached to one other carbon, this is primary. With 2 carbons, it's secondary alkyl halide, and with 3, it's tertiary. So if we look at this example here, we can see that Cl in the blue box, that carbon is attached to 2 other carbons. So this is secondary, or a secondary chloride. The iodide here is connected to 1, 2, 3. So this is a tertiary iodide. And this red carbon here has just the 1, so this is a primary fluoride. Dexamethasone is a halogen-containing steroid that's used to treat inflammation in rheumatoid arthritis or other conditions. So our job is to classify the alkyl halide as primary, secondary, tertiary, and also the alcohol groups. So our alkyl halide is just this F here. This carbon is bonded to 1, 2, 3. So that one is tertiary. The alcohol over here is primary. This one is 1, 2, 3, that's tertiary. And this alcohol here is, we'll use triangles, 1, 2, so that one is secondary. Alkyl halides are polar because of the lone pairs, and they're also electronegative. They are generally pretty insoluble. And the boiling and melting point is slightly higher than alkanes that are similar in mass. Okay, so the boiling point of chloroethane is 12 degrees. For chloropropane is 47 degrees. So we're increasing carbons here. And then for 1-bromopropane, which has the larger electronegative atom, so it's more polar, this one is 71 degrees Celsius. So as we increase the size of the alkyl group and the size of the halogen, that increases the boiling point. In order to name alkyl halides, you want to find the carbon parent chain containing the carbon bonded to the halogen, and then apply all other rules. So here we have a chlorine. This is at 2. So this would be 2-chloro-5-methyl heptane. And in a cyclic structure, we have a chloro versus a methyl. And either way I number, it's going to be tied. So this will just get the priority because it comes first alphabetically. And this will be cyclohexane. All right, here we're going to give the structure corresponding to this name. I like to start with the parent, this octane. There's 2 methyl groups at 2. 4 has an ethyl, and 5 has an iodo. So we'll put an I there. Alkyl halides are excellent solvents because they're not flammable. They dissolve many organic compounds. However, they can be toxic if inhaled or ingested. Chloromethane is made by kelp and algae. So you can see the structure there, CH3Cl. This is also found in volcano emissions. Dichloromethane is a common solvent in organic chemistry, and this one can actually be used to decaffeinate coffee. Coffee is decaffeinated also with liquid carbon dioxide or dry ice. We're going to classify the circled functional groups in fluticasone, which can be used as an aerosol inhalation to treat seasonal and recurring allergies, and also with chronic lung inflammation in asthma. So this alcohol here is attached to 2 carbons. This is secondary. The fluorine here is tertiary. And this last fluorine is secondary. Chlorofluorocarbons were used many, many years ago in the 50s for air conditioning and other refrigerants, but they have caused lasting harm to the environment because they are inert and non-toxic. They were previously used for refrigerants, solvents, and aerosols. They have a low boiling point and are water insoluble. Our ozone protects Earth's surface, but the reactive intermediates of the CFCs can be decomposed and they convert ozone to oxygen. And a decrease in the ozone concentration will decrease our protective layer and give us some immediate consequences, including increase in incidence of skin cancer and eye cataracts. Other long-term effects include a reduced immune response, interference with photosynthesis in plants, and harmful effects of the growth of plankton, which is a mainstay of the ocean food chain. So these hydrofluorocarbons are an alternative to the chlorofluorocarbons. They decompose more readily before reaching the upper atmosphere, and they're also less destructive to the ozone layer. So you can see two of these different compounds here. We'll take a look at compounds that have sulfur in them. We have the sulfitryl group, which is also known as a thiol. Ethane thiol is a compound that is bent, just like water. And because of those lone pairs, that's why it is bent. Thiols are polar. They are insoluble. Their boiling point is slightly higher than alkanes of similar rate. We don't have hydrogen bonding here. So ethanol's boiling point, because of hydrogen bonding, is around 78. And for ethane thiol, the boiling point is only 35. So having that hydrogen bonding, which you've seen many times now, will really increase the intermolecular forces. And the hydrogen bonds are the stronger type of intermolecular force. But because we can't hydrogen bond in thiols, there are weaker intermolecular forces here. When you're naming thiols, you name the parent hydrocarbon as an alkane and then add the suffix thiol and then number the carbon to give the thiol the lower number. So this is 1. We have 7-ethyl 2-nonane thiol. And this will be cyclohexane thiol. And then 3-methyl 3-sulfonyl 1-hexanol is responsible for the onion-like odor of human sweat, which you can see the structure of there. And then this disulfide is diallyl disulfide, which forms by the decomposition of allicin when garlic is cut or crushed. Thiols can be oxidized to form disulfides. So in this case, you have 2 molecules of ethane thiol. It's going to form a new bond to another molecule of that, and we get this disulfide. So we have a new SS bond, and reducing that disulfide will result in the thiols. So you get a new SH bond. The chemistry of thiols can determine properties and shape of proteins, which we'll see in later chapters. And for some compounds that contain sulfur, if you have naturally curly hair, you have a lot of disulfide bonds in your hair, so the cysteines from the different amino acids. If you have straight hair, you have these different disulfide bonds. We can reduce them to the thiols and then oxidize them to reform the disulfide bonds in the shape of curly strands of hair. So that's how you can get curly hair. If you have naturally curly hair, those disulfide bonds are already existing. So when you're getting a perm, you can turn your hair around those curlers, force the thiols together, and then apply the oxidizing agent.